So we've wrapped up our discussion on continuous time Fourier series. Now it's time to move on to the discrete time counterpart, so discrete time Fourier series. Now, before I go there, I just want to give you a quick review of some of the things that we've actually discussed in the beginning of the semester. So we're going to just quickly review discrete time complex exponential. So you recall discrete time complex exponential is of this form here, which is e raised by j omega naught n, where n is, of course, an integer. There are a few things that we need to remember in the sense how the discrete time complex exponential is different than the continuous time counterpart. So the first thing I want to talk about is the wraparound effect of the frequency in discrete time. So let's consider a discrete time complex exponential, which is x1, which has a frequency of omega naught. And let me just consider another discrete time exponential, which is x2, which has a frequency not of omega naught, but rather omega naught plus some integer multiple of 2 pi, where m therefore is any integer. And if I just expand this out a bit, it turns out that this is e raised to power j omega naught times n times e raised to power j 2 pi times m, which is an integer, times n, which is an integer. And since mn is an integer and n as well is an integer, we can immediately conclude that this thing must be equal to 1. And if this is 1, what we see here is that this x2 of n is e raised to power j omega naught n, which is nothing but x1 of n. So the conclusion that we have, and we know as well, is that the frequency of omega naught is actually equivalent to the frequency omega naught plus any integer multiple of 2 pi. So omega naught is actually the same frequency as omega naught plus 2 pi m. So the frequencies are therefore not unique in discrete time as opposed to the continuous time counterpart. Now, one of the ways, another way, so this is a mathematical way of showing what I just said. Let me try to give you very quickly an intuitive explanation of why something like this goes on. So for that, we're going to try to visualize a discrete time exponential so the signal itself, which is actually a three-dimensional visualization in the sense that there's one axis which corresponds to time, and then there are two other axes. One of them corresponds to the real part of the signal, and the other one to the imaginary part of the signal. So for ease of visualization, let me collapse the dimension of time. So if this dimension, looking into the screen, for example, or looking out of the screen is time, and you're just looking at the signal, how it behaves if the on the screen itself. So there's a projection of the signal as you will see on the screen. So for that two-dimensional visualization, let this axis be the real part of x of n, this axis be the imaginary part of x of n. So this is the real part of x of n. This is the imaginary part of x of n. And as n increases, it's easy to see that x actually moves as samples on a unit circle. So those samples are going to reside on a unit circle. All right. So when n equals 0, so let's say for ease of understanding, let's consider x1 of n, which has a frequency of omega naught, which is just is frequency of just pi by 2 radians per sample. So when n equals 0, the signal is going to be over here. You're going to see the signal residing here, when n equals 0. When n equals 1, the signal would have actually traversed. It's actually moving on the circle. It's such that you're going to see it having traversed an angle of pi by 2 radians. So this is where n equals 1 is going to be. N equals 2 is here, which is an angle of pi radians, and then 3 pi by 2 is n equals 3, and n equals 4 is going to be back where it started out, and that immediately makes it clear that the period for this signal is 4 samples. If I give you x2, let's say that's another signal which does not have a frequency of pi by 2, but rather a frequency of pi by 2 sum plus 2 pi. And from the analysis that I see above, x1 and x2 must be the same. But let's just take a visual look at what happens here. So small n equals 0, your x2 of n1 starts out at an angle of 0. So this is exactly where the yellow signal was. This is where n equals 0. Now at n equals 1, the total angle that the signal is going to traverse is 5 pi by 2 radians. So pi by 2 plus 2 pi is 5 pi by 2 radians. And at n equals 1, so the signal is going to traverse a whole revolution of 2 pi radians, and then on top of that, another pi by 2 radians. So it's going to be back smack where n equals 1 signal was at this particular time. So even though it's actually completed an entire revolution, it's just that when you're looking at the signal at n equals 1, you're not really been able to observe whether or not it has been able to complete a full revolution. So this is where you're going to see the signal at n equals 1. Similarly, at n equals 2, the signal is going to traverse 2 pi radians plus pi by 2 radians. So this is where the signal is going to be, and n equals 2, exactly where the yellow signal was. Similarly, this is where the signal is going to be at n equals 3, and so on and so forth. And this signal will also have a same period of 4 radians per sample. So the bottom line, therefore, from not only that we can conclude from not only from the analysis up above, but also from this intuitive explanation here, is that the frequencies in discrete time are not unique. Another way I can present this is if I have a linear axis on which I am representing the frequency. So this is where this axis represents the frequency. Let this frequency be 0. Let this frequency be 2 pi. And what we just conclude from up above is that if there's a certain frequency which resides, let's say over here in the interval 0 to 2 pi, and let's say that is omega naught, that omega naught is exactly the same frequency that I would get here, so which is omega naught plus 2 pi, and which is exactly the same frequency as I would have over here, which is omega naught plus 4 pi, and so on and so forth. And similarly, on the negative side as well, so there's, if this is 2 pi and this is omega naught minus 2 pi, the frequency that I observe at omega naught by 2 pi is in fact exactly the same frequency as omega naught. So there are no so the unique frequencies, therefore, in discrete time only reside in the interval of length, which is 2 pi radians. And that's why it suffices for us to consider frequencies which are only in an interval of 2 pi. And by convention, majority of the times, we would therefore, so we limit that interval by convention to either to 0 and 2 pi. So we'd always consider the frequency in discrete time either in the interval 0 to 2 pi, or in some cases, you'll see that they're going to be residing in the interval minus pi to pi. And that's enough, because every frequency that resides out of this interval is in fact wraps around and comes back and exactly the same frequency that you have inside this interval. So bottom line, frequencies in discrete time are not unique. It suffices to just consider frequencies in any interval of length 2 pi, but by convention, and for ease of understanding, the frequencies that we do consider are majority of the times only going to be within the interval 0 to 2 pi, or in some cases between minus pi to plus pi. So the next thing we want to address is how does the rate of oscillation of a discrete time complex exponential changes as I start increasing the frequency. And this behavior is not exactly the same as we have in the continuous time counterpart. So what I mean by that is, let's say I have the frequency axis here, and this maybe is a frequency which is 0 radians per sample. This is 2 pi radians per sample. I the question I want to ask is, if I start increasing the frequency from 0 all the way up to 2 pi, does that result in an increasing rate of oscillation in the complex exponential? And a little bit more in-depth thinking or observation would yield a negative answer. Why? Because we know from up above, just what we saw earlier, is that frequency of 0 is actually exactly the same as the frequency of 2 pi radians per sample. So 2 pi radians per sample is exactly the same as the frequency of 0 radians per sample. And 0 frequency corresponds to a flat DC signal which just stays 1 for all time instances, and therefore it's not really oscillating at all. And 2 pi is exactly the same as well. So it cannot really be a monotonically increasing rate of oscillation. So the question we want to then ask is, what is the maximum frequency in discrete time? So in order to address that, let me just consider two frequency. Let me consider a frequency which is omega naught here. Let me consider another frequency which is 2 pi minus omega naught. In other words, this gap is omega naught. So let me try to see what those complex exponentials turn out to be. So if x1 of n is a discrete time exponential which has a frequency of e raised by j omega naught n, and x2 of n has a is discrete time exponential which has a frequency of 2 pi minus omega naught times n, I clearly see that this is e raised by j 2 pi n times e raised to power minus j omega naught n. And I know from what we've done earlier, this is equal to, this thing is equal to 1. This is equal to 1, and therefore this x2 of n is really nothing but e raised to power minus j omega naught n. So therefore, the signal corresponding to the frequency omega naught and the signal corresponding to frequency 2 pi minus omega naught has more or less the same frequency omega naught, except the only difference being that one of them rotates in a clockwise direction, in a counterclockwise direction, and the other one rotates in a counterclockwise direction. But the period for those, if it's periodic, is going to stay the same for both complex exponentials. And therefore, the rate of oscillation, the number of samples it takes, to complete one revolution, regardless of what direction I'm really revolving in. The number of samples it takes to complete one revolution is going to stay the same for both signals as well. And therefore, if I were to plot some rate of oscillation, so let's say this is x-axis is the frequency, and the y-axis is something called the rate of oscillation. Even though I've not explicitly define what this is. It's just as a hand waving thing is just the rate at which the signal oscillates, or the inverse of the number of samples it takes to complete one revolution. So what we've figured out from over here is that if I pick a frequency which resides over here, and which, for example, may result in an oscillation which looks like this, if this is omega naught, and there's another frequency which is 2 pi minus omega naught, which exactly gives you the same rate of oscillation. So the rate of oscillation is actually, therefore, that means if the rate of oscillation starts increasing over here, as it starts increasing over here, I would expect that the rate of oscillation is going to start decreasing over here as well because of the symmetry. And this increases, this decreases in the negative direction, and they're going to meet smack in the middle, which is pi radians per sample. And I would expect that this at pi radians per sample, this is where the maximum rate of oscillation is. So based on this sort of hand waving analysis, I can I conclude that the discrete time exponential of maximum frequency of max frequency is x of n, which is equal to e raised to power j pi n. And really, a little bit of more thought reveals that this should really be the discrete time exponential with the maximum frequency. That no other discrete time exponential should have that maximum frequency. Why? Because if this e raised by j pi n is just nothing but minus 1 raised to power n. And if I were to sketch this out, if I were to sketch this e raised to power minus j pi, e raised to power j pi by n, which is just minus 1 raised to power n, what I observe is that n equals 0, this signal is 1. But n equals 1, it goes smack down to bam, minus 1. And right at the next instant, which is 2, it goes back up to 1 and goes on oscillating. And this is the maximum sort of change that I can expect in a discrete time signal. Another one of the ways you can see that this is really, so this is minus 1 raised to power n, where this is n. So minus 1 raised to power n is this signal here. So another one of the ways you can really see that this should really be the fastest oscillating discrete time exponential is because the period for this signal is 2. And indeed, the minimum period that you can expect of a periodic discrete time exponential is 2. There's no other discrete time exponential which can have a smaller period than this. You could say, you know, that might be a signal with a period of 1. But if there's a discrete time signal which has a period of 1, think about that. That's nothing but a constant signal, which just stays constant. So one final point I want to make here in this subsection is that if this is the free, so there's the frequency in discrete time is there's sort of a circular aspect to it, and the reason why I say that is if this is frequency 0 and this is 2 pi, 2 pi is actually nothing. 2 pi is nothing but the same frequency as 0. So if I go on and move further up from 2 pi and go up to 4 pi, what I'm really doing is I'm going back. So this 2 pi is exactly the same as 0. This thing here, this frequency, for example, here is exactly the same as this frequency. This frequency here is exactly the same as this frequency. So I exactly am going around in circles. So in some sense, what we're saying is that the frequency in discrete time are actually circular. So if this is frequency of 0, this point here, I start increasing the frequency. I increase the frequency, and as I go on to 2 pi, I get back where to 0 was. As I go on further moving up the frequency, I've actually stuck in that loop where the frequency is being increased from 0 to 2 pi, and then from 0 to pi over and over again. One final point I want to mention, even though it's not really very related to what we're going to discuss in this module, but nevertheless, I'm just going to mention for the sake of completeness, is that a discrete time complex exponential is not always periodic as opposed to its continuous time counterpart. And just very quickly, I'm going to show you why is that true. Is the reason why it's true is because for x of n to be periodic, there has to exist some integer n so that x of n equals x of small n plus capital N. So there needs to exist some integer capital N which satisfies this condition. So this implies that e raised to power j omega naught n must be equal to e raised to power j omega naught n plus capital N, so that which is e raised to power j omega naught n times e raised to power j omega naught times capital N. And therefore, for that integer capital N, this must be e raised to power j omega naught capital N. This must be equal to 1. So therefore, if the signal is to be periodic, there must exist some integer capital N. There must exist some integer capital N so that this exponential term turns out to be equal to 1. And I know that this must imply that there must exist some integer. So there must exist um, some integer N which is in which is not n is not equal to 0, such that omega naught times capital N is some integer multiple of 2 pi. And for this to be true, you need, so this will only be true when omega naught by 2 pi is actually a rational number. So therefore this implies that omega naught plus my divide by 2 pi must be equal to some small m divided by n. So for that integer small m and for that integer capital N to exist, omega naught divided by 2 pi must be of a rational form. If it is not of a rational form, this exponential, discrete time exponential will not be periodic. And a counter example, of course, is what if, for example, omega naught was equal to 6, and you can immediately see 6 divided by 2 pi is not a rational number, and therefore this discrete time exponential is not periodic.